Hey guys, it's Murat Duman here. In this video series, I'm gonna talk about differential equations. Our textbook is Elementary Differential Equations and Boundary Value Problems. Its writers are Boyce and Di Prima. Today I will talk about the introduction part, which consists of some basic mathematical models, solution of some differential equations, and classification of differential equations. Our first example is modeling a falling object with air friction using differential equations. From Newton's second law, we know that force is equal to mass times acceleration. The unit of F is Newton, the unit of M is kilogram, and unit of A is meter per second square. For falling object, A is equal to G, which is 9.8 meter per second square. So, for a falling object, F, gravity, let's say, is equal to M times G. This formula is valid when there is no air friction. But in our example, air friction exists. And let's assume that air friction is proportional to speed. So, F friction is equal to some constant, let's call it gamma, times V. So, net force is equal to F gravity minus F friction. F gravity is equal to M times G, and F friction is equal to gamma times V. F net is equal to M times A. Acceleration is the first derivative of speed, so F net is equal to M times dV over dt. By dividing both sides by M, dV over dt is equal to G minus gamma over M times V. This is the differential equations that we look for. What about the unit of gamma? By investigating this differential equation, we can find the unit of gamma. The unit of gamma times V must be equal to unit of M times G. Unit of M times G must be equal to unit of gamma times V. Unit of mg is equal to kilogram times meter per second square. It must be equal to unit of gamma times unit of speed, which is meter per second. From here, it is found out that unit of gamma is equal to kilogram per second. Let's continue from this equation. Let's put in some numbers. Let's say M is equal to 10 kilogram and gamma is equal to 2 kilogram per second. So dV over dt is equal to 9.8 minus 2 over 10, which is equal to 0.2 times V. At this point, we will define equilibrium point. Equilibrium point is the point where no change occurs in the derivative. So in our example, by putting 0 for dV over dt, 0 is equal to 9.8 minus 0.2V. From here, V equilibrium is equal to 49 meter per second. Let's sketch the graph of speed. Time, t, speed, v. And here is our equilibrium point. Equilibrium point, which is 49 meter per second. Let's turn back to our equation. If the value of speed is bigger than the value of equilibrium point, this value will be negative. So the derivative value will be negative. So the speed value will be decreasing, and as time goes to infinity, the value of speed will be equal to equilibrium point value. And for the opposite case, if the value of speed is less than the equilibrium point value, this value will be positive. So the derivative value will be positive. And as time goes to infinity, the value of speed will be increasing. And at time goes to infinity, the value of speed will be equal to equilibrium point value. So our graph will be look like this. So for the speed values that are bigger than the equilibrium point value, the value of speed will be decreasing in time. And as time goes to infinity, the value of speed will be equal to equilibrium point value. And for the opposite cases, the speed value will be increasing in time, and as time goes to infinity, the value of speed will be equal to equilibrium point value. For our next example, we will investigate the mice population in the existence of the owl population. First of all, we will investigate the mice population when there is no owl around, just like the falling object example. In the falling object example, we first investigate the situation when there is no air friction. In the absence of predator population, mice population will increase proportional to current mice population. Let's assign P for mice population. And the increase in mice population will be proportional to the current mice population. So dp over dt will be equal to some constant, let's call it r, times p. In the absence of predator population, this differential equation seems very logical, but not that logical, because the current mice population will not increase linearly. Sooner or later, there will be shortage of food or space. But for the sake of simplicity, we can still use this differential equation. By the way, R is the constant growth rate. Constant growth rate. What is the unit of R? Unit of R times P must be equal to unit of dP over dt. So, unit of dP over dt must be equal to unit of R times P. Unit of dP over dt is equal to number of mice per unit time. And unit of P is equal to number of mice times unit of R. From here, we can find out that unit of R is equal to some constant over time. And now we must find a suitable unit for time. We can choose second or minute as a unit of time. But in a limited area, number of miles that killed by owls per second or per minute will be very low. So it will make more sense to choose the unit of time as day or month. And now we can consider the number of miles that are killed by owls. Let's say 15 miles per day are killed by owls. And let's assign a value for R. R, let's say, is equal to 0.5 per month. Since we choose month as a unit of time, we must consider the number of miles per month that are killed by owls. That number is equal to 30 times 15, which is equal to 450. This is the number of mice which killed per month. And now we can complete our differential equation. In the absence of predator, our differential equation was dp over dt is equal to r times p. By the way, we chose 0.5 per month for r. And now we must consider the existence of owls. Owls kill 450 mice per month, so we must extract this number. Now our differential equation is dp over dt is equal to 0.5 times p minus 450. And let's find the equilibrium point. 0 is equal to 0.5p minus 450. We chose 0 for dp over dt in order to find the equilibrium point, where no change occurs. So, p equilibrium is equal to 900. Now, let's sketch number of mice via time. Time, its unit is month, and number of mice, which is p. And let's mark our equilibrium point. 900 is in our example p equilibrium. Let's turn back to our differential equation. If this number is bigger than 900, then this number will be positive. So dp over dt will be positive. So as time passes, number of mice will diverge from the equilibrium point, which is 900. Now let's consider the opposite case. If this number is smaller than 900, which is our equilibrium point, then this value will be negative. So dp over dt will be negative. And as time passes, the number of mice will decrease and the number of mice will diverge from the equilibrium point. So our graph will look like this. Now let's solve some problems. In this problem, the general form of the differential equation is given by dy over dt is equal to a times y plus b. We are asked to find all solutions that are approaching to 3. All solutions are approaching to 3, that's why our equilibrium point is equal to 3. And let's sketch the graph of y via t. 3 is our equilibrium point in this example. And since all the solutions are approaching to 3, our graph will look like this. The y values that are bigger than 3 are decreasing in time. So, first derivative of the y values that are bigger than 3 is negative. And the opposite case, where the y values are smaller than 3, are increasing in time. So first derivative of the y values that are smaller than 3 is positive. Let's write it down. For y values that are bigger than 3, dy over dt is smaller than 0. For y values that are smaller than 3, dy over dt is bigger than 0. In order to ensure this condition, our differential equation should be looked like this. dy over dt is equal to minus y plus 3. Let's test our differential equation by taking two values. First one is y is equal to 2.9, which is smaller than the equilibrium point. So dy over dt is equal to minus 2.9 plus 3, which is positive. And let's take the second value as 3.1. dy over dt is equal to minus 3.1 plus 3, which is a negative value. So, as it is seen from these values, dy over dt is positive for the y values which are smaller than 3, and dy over dt is negative for the y values which are bigger than 3. So our conditions are met. In this problem, again, the general form of the differential equation is given by dy over dt is equal to ay plus b. We are asked to find all solutions that are diverging from y is equal to 2. Since it is said that all solutions are diverging from y is equal to 2, our equilibrium point is equal to 2. So, if we were sketched to our graph, it should be look like this. 2 is our equilibrium point, and all solutions are diverging from equilibrium point as it is said. Let's write down the conditions for y values that are bigger than 2, dy over dt is positive, and for y values that are smaller than 2, dy over dt is smaller than 0. In order to meet these conditions, our differential equation should be look like this. And let's test this differential equation again by taking two values. One of the values is bigger than equilibrium point and the other is smaller than the equilibrium point. So let's take the values as y is equal to 2.1 and y is equal to 1.9. And let's write down the equations. Dy over dt is equal to 2.1 minus 2, which is positive, and dy over dt is equal to 1.9 minus 2, which is negative. As it is seen from here, for the y values that are bigger than the equilibrium point, the first derivative is positive. And for the y values that are smaller than the equilibrium point, the first derivative is negative. So our conditions are met. In this problem, this is our differential equation and we are asked to determine the behavior of y as t goes to infinity. By the way, y prime is the another representation of dy over dt is equal to y times 4 minus 1. Here there are two equilibrium points. One of them is y is equal to 0 and the other one is y is equal to 4. As it is seen from the differential equation, there are three intervals that we will look for. And these intervals are for y is bigger than 4, for y is between 0 and 4, and for y is less than 0. In this region, y prime is negative, and in this region, y prime is positive, and in this region, y prime is negative. And let's sketch this graph. This is y, this is t, and there are two equilibrium points. One of them is y is equal to 0, and the other one is y is equal to 4. This is, let's say, v equilibrium 1, and this is v equilibrium 2. And let's say this is the first region, this is the second region, and this is the third region. In region 1, y prime is negative. So, as time passes, y values will converge to v equilibrium 2, which is 4. And in region 2, y prime is positive. So, the y values that are between 0 and 4 will converge to v equilibrium 2, since y prime is positive. And in region 3, y prime is negative. So in region 3, since y prime is negative, the y values that are smaller than 0 will diverge from 0. So let's write down what we have found. In region 1, solutions approach 4 from above. And in region 2, solution grows to 4 as time goes to infinity. And in region 3, solutions diverge from 0. In this question, the differential equation is given as y prime is equal to y squared, and we are asked to determine the behavior of y as time goes to infinity. As it is seen from the differential equation that our equilibrium point is 0. And dy over dt is positive for all y values, since y prime is equal to y squared. And let's sketch the graph of this differential equation. Y equilibrium is 0, and this is our, let's say, first region, and this is our second region. In first region, y prime is positive. So, the y values that are bigger than 0 will diverge from 0 as time passes. And for the second region, y prime is again positive. So, the y values that are smaller than 0 will converge to 0 as time passes, since y prime is positive. So our graph will look like this. Let's examine this question. A pond initially contains 1 million gallons of water and unknown amount of undesirable chemical. So this is our pond, and initially it contains 1 million gallons of water. And this 1 million gallons of water contains some pure water plus some chemical. Water containing 0.01 gram of this chemical per gallon, and water flows into the pond at a rate of 300 gallons per minute. So, for each minute, 0.01 gram per gallon times 300 gallons per minute gram of chemical will flow into the water, which is equal to 3 grams per minute. Let's turn back to question. The mixture flows out at the same rate, so the amount of water in the pond remains constant and the chemical is uniformly distributed throughout the pond. So 300 gallons of water will flow into the pond in each minute. And the same amount of water will flow out of the pond in each minute. And let's assign the letter Q to the amount of present chemical in the pond. We don't know the exact amount of chemical in the water yet, but since in the question it is said that the chemical is uniformly distributed in the pond, the amount of chemical that is flow out in each minute is proportional to the water that flows out over present amount of water in the pond times Q. This is equal to the amount of chemical that flows out of the pond in each minute. We can easily find out the amount of chemical that flows out of the pond in each minute easily by using this ratio, since the chemical is uniformly distributed in the pond. Let's turn back to this ratio. The water that flows out of the pond is equal to 300 gallons of water per minute. And the present amount of water in the pond is equal to 1 million gallons. Times Q is equal to the amount of chemical that flows out of the pond in each minute. So we have found out here that 3 grams of chemical will flow into the pond in each minute. And here we have found out that 300 over 1 million times Q gram of chemical will flow out of the pond in each minute. Let's turn back to the question. Write a differential equation whose solution is the amount of chemical in the pond at any time. The change in the amount of chemical is represented by dq over dt. And the amount of chemical that flows into the water is constant and it is equal to 3 grams per minute. And the amount of chemical that flows out of the pond in each minute is equal to 300 over 1 million times Q gram of chemical substance. This is the differential equation that we look for. This was A. Let's turn back to the question. How much of the chemical will be in the pond after a very long time? Does this limiting value depend on the initial chemical? Here we are asked to find the equilibrium point, because equilibrium point is the point where the function converges after a very long time. In order to find the equilibrium point, we will put 0 instead of dq over dt. 0 is equal to 3 minus 300 over 1 million Q. And from here we will find out that Q equilibrium is equal to 10 kg. And in the continuation of the problem we were asked that if this limiting value depends on the initial chemical or not. Let's sketch the graph of given differential equation. Our equilibrium point in this question is equal to 10 kg. If the final value of the chemical substance doesn't depend on the initial value of it, our graph should be look like this. As it is seen from here, whether the initial value of the chemical substance is bigger or less than the equilibrium point, it will converge to the equilibrium point, which is 10 kg. Let us test this condition whether it is true or not. We will take two values in order to test these conditions. First value is smaller than the equilibrium point, which is, for example, 5 kg. And let's put this number to our differential equation. dq over dt is equal to 3 minus 300 over 1 million times 5,000. As it is seen from here, this value is positive. So, dq over dt is positive in this region. And let's take another value which is bigger than the equilibrium point this time. Let's say q is equal to 15 kg this time, which is bigger than the equilibrium point. So dq over dt is equal to 3 minus 300 over 1 million times 15,000. This time this value will be negative. So dq over dt in this region will be negative. As it is seen from here, the graph that we sketched met these conditions. So whether the initial value of the chemical substance is bigger or less than 10 kg, it will sooner or later converge to the equilibrium point, which is 10 kg. So final value of the chemical substance doesn't depend on the initial value of it. Next question. A spherical raindrop evaporates at a rate proportional to its surface area. Write a differential equation for the volume of the raindrop as a function of time. Since we are said that a spherical raindrop evaporates at a rate proportional to its surface area, we can write this differential equation. dv over dt is equal to some constant, let's say k times s. Here s is surface area and V is volume. As time passes, the volume of the raindrop will get smaller and smaller. So the slope of the function is negative. For this reason, there should be a minus sign here. This is the slope of the function. In order to keep one dependent variable in our differential equation, which is volume here, we can write the surface area in terms of the volume. The volume of a spherical raindrop is equal to 4 over 3 pi r cube. R is radius here. And the surface area of a spherical raindrop is equal to 4 pi r square. You can write S in terms of V like this. If you do this operation, you will see that it holds. This term here is actually a constant and we can call it, let's say, b. So, s is equal to v to the 2 over 3 times b. And let's put this in our differential equation here. dv over dt is equal to minus k times v to the 2 over 3 times b. This is equal to minus k times b times v to the 2 over 3. This term is another constant and let's call it as c. So, dv over dt is equal to minus c times v to the 2 over 3. This is the differential equation that we look for. And here c is bigger than 0. In this part we will see the solution of some differential equations. Let's remember the differential equations that we wrote at the beginning of this video. First differential equation belongs to the fallen object example. dv over dt is equal to mg minus gamma v. Let it be our first differential equation which belongs to the fallen object example. And our second differential equation is dp over dt is equal to rp minus k, and let it be our second differential equation which belongs to the mice and owls example. If you examine carefully, you will see that the general form of these differential equations are like this. Let it be our third differential equation. And this minus not really that important, it can be plus anyway. And let's remember the exact differential equation that we wrote for the mice and owls example, which was dp over dt is equal to 0.5 times p minus 450. We can rearrange this equation and write like this. And if we integrate this equation, we will get and absolute value of p minus 900 is equal to e to the t over 2 times e over c. And this absolute value sign here is not really that important, because due to the absolute value sign there will be a plus or minus sign here, and we can put it that plus or minus sign in front of this constant e to the c, and plus or minus e to the c is again another constant, and we can still write that number as another constant like c. So p minus 900 is equal to e to the t over 2 times c. So p is equal to 900 plus e to the t over 2 times c. And in order to find the equilibrium point, we will put 0 for dp over dt. And from here we will get 900 for our equilibrium point. And let's sketch this differential equation. P versus T, and 900 is our equilibrium point in this example. And according to the value of C, our curve can be any of these curves. Because here the sign of C can be plus or minus. In order to get the exact curve which is related to our differential equation, we need extra information, which is called the initial value. It is necessary to find the exact curve. Here let's say the initial value of P is equal to 850. And the problem will turn into an initial value problem. By putting 0 here in our differential equation, we will get P0 is equal to 900 minus 50 times e to the t over t. From here we get the exact differential equation, and we found that c is equal to minus 50. Let's turn back to our general differential equation. dy over dt is equal to a times y minus b, and it was our third differential equation. Rearranging this differential equation, we get dy over y minus b over a is equal to a. From here, by integrating both sides, we get ln absolute value y minus b over a is equal to a times t plus c. From here, y minus b over a is equal to e to the a times t times e to the c. And this is again a constant, so we can call this c. So y is equal to b over a plus e to the a times t times c. This is the general solution, and it contains all solutions. As I mentioned in the previous example, we need an initial value to find the exact solution. So we need the initial value of the function to find the exact solution, and that is the y0 or y0 value. So putting y0 value in our general differential equation, y0 is equal to b over a plus c. From here, c is equal to y0 minus b over a. We will use this c value in our general solution. So y is equal to b over a plus y0 minus b over a times e to the at. And this is the final equation that we look for. And at the same time, this is the solution or the initial value problem. Again, we need this initial value for the exact form of our differential equation. Let us summarize what we get. Our general form of the differential equation is general differential equation is in the form of dy over dt is equal to a times y minus b, and the general solution that we get is in the form of y is equal to b over a plus y0 minus b over a times e to the at. By using this relation between general form of differential equation and its general solution, we can solve any differential equation in this form. For example, let's take the differential equation that we got in mice and owls example. It was dp over dt is equal to r times p minus k. Here, p corresponds to y and R corresponds to A and K corresponds to B in general differential equation. Let's write this down. So P is equal to K over R plus P0 minus K over R times e to the RT. And let's take the fallen object example. In the fallen object example, we got this differential equation. Fallen object. It was dv over dt is equal to g minus gamma over m times v. And here v corresponds to y, g corresponds to minus p, and minus gamma over m corresponds to a. Let's write it down. Y corresponds to v, a corresponds to minus gamma over m, and b corresponds to minus g. So solution of the fallen object example will be v is equal to mg over gamma plus v0 minus mg over gamma times e to the minus gamma over m times t. And let's solve some problems. Our first problem is a radioactive material disintegrates at a rate proportional to the amount currently present. dq over dt is equal to minus r times q. R is bigger than 0. There is a minus sign here in the differential equation since the material in the problem is given radioactive. So the amount of radioactive material will decrease in time. So if 100 mg material decays to 82.04 mg in 1 week, find R value. So let's first solve the differential equation. dq over dt is equal to minus r times q. So dq over q is equal to minus r times dt. Let's integrate both sides. ln q is equal to minus rt plus c. Q is equal to e to the minus rt times c. And Q0 in the problem is given as 100 mg here. So 100 is equal to C. Because here if we put 0 for T, Q0 will be directly equal to C, which is 100. So by putting 100 here for C, we can write Q is equal to 100 times e to the minus RT. And after 1 week, Q will be equal to 82.04 milligram, which is equal to 100 times e to the minus R. From here, we get 0.1980 per week. In this problem, a circuit is given which consists of a power supply, a resistor and a capacitor. And the differential equation for this circuit is given in this form. You may or may not be familiar with where this differential equation comes from, because it requires a little bit of circuit theory knowledge, and at this point it really doesn't matter whether you know or don't know where it comes from. Just use it and try to solve this problem. First of all, we will make the factor in front of the highest order term 1. By the way, I should have given the order definition at the beginning, but anyway, I can give it now. The order of a differential equation is the order of the highest derivative that appears in the equation. For example, in this differential equation, the highest order is 1 because the derivative of q is taken just once with respect to t. So, in order to make the factor which is in front of dq over dt 1, we will divide both sides by r. So, dq over dt plus q over rc is equal to v by r. And from here, dq over dt is equal to vc minus q over r. And dq over q minus vc is equal to minus dt over r. By integrating both sides, ln q minus vc is equal to minus d over r plus k. K is the constant here. From here, q minus vc is equal to e to the minus t over r times k. And q is equal to vc plus e to the minus t over r times k. And in the problem, q0 is given as 0. And we will use this initial value in order to identify the exact value of the constant k. So by using this initial value in our differential equation here, q0, which is 0, is equal to vc plus k. And from here, k is equal to minus vc. By using this k value in our equation again, q is equal to vc minus vc times e to the minus t over r. And q of t is equal to vc times 1 minus e to the minus t over r. This is the solution that we look for. And in A, we are asked to find q of t and plot it versus time. T, q, and cv is the constant here. As time passes, the q value will be close to the constant vc value, like here. And in B, we are asked to find the limiting value of q. By limiting value, we are asked to find the equilibrium point. As I mentioned before, equilibrium point is the point where no change occurs in the function as time goes to infinity. So we are asked to find the value of q at infinity. I said no change in the function, so I will put 0 in dq over dt here. So q over rc is equal to v over r. Q over rc is equal to v over r. From here, the q value at infinity will be equal to vc. So the equilibrium point is vc. And let's look at C. After a very long time, battery is removed from the circuit at t is equal to t1. Find qt for t is bigger than t1 and sketch its graph. Let's turn back to our differential equation, and here V will be equal to 0 since the voltage source is removed. So our differential equation will be dq over dt plus q over rc is equal to 0. And from here, dq over dt is equal to minus q over rc, and dq over q is equal to minus dt over rc. By integrating both sides, ln q is equal to e to the minus t over rc times k. In order to find out the value of constant k, we need to solve an initial value problem. Since in the question it is said that battery is removed after a very long time, q value will be very close to the constant cv value as it is seen from this graph. From here, Q of t is equal to e to the minus t over rc times k, which is Cv. We can divide this question into two parts. First, battery is in the circuit, and the second part is battery is removed from the circuit. And this is the timeline, let's say. Here t is equal to 0, and in the question it is said that battery is removed at t is equal to t1 here. So Q value at t equal to 0 is our first initial value, which belongs to the first part of the problem. And Q value at t equal to t1 is our initial value, which belongs to the second part of the problem. Since we are now dealing with the second part of the question, where battery is removed at t is equal to t1, we must behave like t is equal to t1 is our new starting point. So, in this equation, we must put t minus t1 instead of t. For treating t is equal to t1 as our new starting point, since Q of t minus t1 is equal to Q of 0 at t is equal to t1. So our solution at the second part will be Q of t is equal to e to the minus t1 over rc times Cv for t bigger than t1. So its graph will look like this. T, Q. This is the first part of the problem. And since it is said that battery is removed at t equal to t1 here, from this equation, which belongs to the second part of the problem, the graph will look like this, since the function is exponentially decreasing. Classification of differential equations. In this part, it is really important to identify if a given differential equation is linear or nonlinear. A differential equation is basically consists of the independent variable t and dependent variable y and its derivatives. And the differential equation f is said to be linear if f is a linear function of the variables y and its derivatives, and otherwise it is nonlinear. What we mean by f is the linear function of the variables? It means the factor in front of the dependent variable y and its derivatives should not be a function of the dependent variable. And let's solve some problems in order to understand what we mean here. Determine the order of the given differential equation and also state whether the equation is linear or nonlinear. And in the first problem, since the order of the highest derivative is 2, it's a second order differential equation. And now let's see if this equation is linear or nonlinear. And since the coefficients in front of the dependent variable y and its derivatives are not a function of dependent variable y, this is a linear equation. And this equation is also a second order differential equation. But since this coefficient in front of this derivative is a function of dependent variable y, this equation is nonlinear. And this is a fourth order differential equation. Fourth order. And since the coefficients in front of the dependent variable y and its derivatives are not a function of dependent variable y, this is a linear differential equation. And this is a first order differential equation. And it is a little bit tricky when it comes to identify this equation is linear or nonlinear, because we can write this term like this. So, as it is seen from here, the coefficient in front of the dependent variable y is a function of dependent variable itself. So, this equation is nonlinear. This is a second order differential equation, and here we see a function of dependent variable y, so this equation is nonlinear. This is a third order differential equation, and this term in front of the dependent variable y is a function of independent variable t, so it doesn't spoil the linearity of these differential equations. And also the other coefficients don't spoil the linearity of the differential equation, so this equation is linear. This is the end of the first video, and in the second video I will talk about the first order differential equations more. And if you like this video, don't forget to subscribe. See you.